Hello, everyone. Welcome to Metaverse. My name is Joe Lee from HDF Group. And yeah, come on in, welcome. I want to ask some question. How many of you have used the Meta Quest 2? 1, 2. So exactly 2 out of 8, which is 25%. I have about 240 Facebook friends, and when I got my Meta Quest 2, I was surprised that I see about 10 friends are already using it, which is really great to know. So yeah, welcome to the Metaverse. If you haven't tried Meta Quest 2 yet, please try. You'll be quite surprised. So why I started this new session? Yeah, as far as I know, I attended several EC meetings. This is the first time that someone talks about Metaverse. And when I applied for this session, I was surprised that it was accepted. Not only that, it was accepted as a Tuesday session. And I'm also surprised to see these many people as a first session. At this point, we are ranked at 31st, but I think it's pretty good ranking in terms of a session ranking as a first session. And is there anyone from USA? USA. Yeah, country USA. Everybody? Okay. How about Illinois? Nobody's from Illinois. Okay. My company HDF is in Illinois, and I'm from Champaign, Illinois. And Illinois had an interesting lawsuit against Facebook because of privacy. And I signed up for the class action suit and recently got about $397 check. I thought it was a spam mail, but it was real. When I deposited, I got the cash. So with that money, I went to Costco and found out that Meta Quest 2 was $399. So there's nothing to lose. Thank you, Mark Zuckerberg. And I got my Meta Quest 2. Okay. I tried several things. What's your favorite app? Okay, how about you? Okay. Yeah, my favorite app was Gorilla Tag. If you haven't tried it, try that first. You'll be impressed. And then I got this big question. What is Earth science in Metaverse will look like? So this is another web that I enjoy the most. Looks like somebody tried that already. And I can really crawl inside the space station with my hands. And I can see this, Earth from the space station. And this is a scene that I really wanted to see from the space station if I become an astronaut. So it was an amazing experience. But something is missing here. And do you think what this will be? Can anyone guess? Okay, probably not. Then we'll go to our speakers to find out what's missing here, okay? And first speaker will be Joe Roberts from JPL, who distributes the real Earth data through the NASA DAX, okay? Can you switch to Joe Roberts?
All right. Can you all see me and see the slides in the conference room on full screen here? I can't hear anyone, but I'll assume that's a yes. So my name is Joe Roberts. I'm a technical lead in the Science Data Visualization Group at the NASA Jet Propulsion Laboratory. I was really hoping to make it in person to ESEP this year, but I had to change travel plans at the last minute. So I'm joining you all from the Metaverse. So I'm going to talk about Earth science data visualization in the Metaverse. So I tend to use the terms augmented reality, virtual reality, or XR, or extended reality, sort of interchangeably with the Metaverse for better or worse. So a lot of this really pertains to technologies that are related to augmented and virtual reality. So with the new technologies that are out there, it's really offering new possibilities for interacting with geospatial data in a collaborative environment. So we do have highly detailed 3D data of the Earth. So we have things like climate and weather models, data that's been collected via orbital radar, sounders, other instruments. And we also have airborne terrestrial LiDAR, so things not in space, but in the air, on the ground, and in situ measurements, so monitors are actually here on the Earth. So the question that I think about a lot is, how can we aid Earth scientists with this new technology? One of the Earth scientists who I work with pretty frequently, Dr. Eric Leroy, he had this quote: "How can we bring this form from a gimmick, a wishful dream, to efficient implementation of virtual reality for science?" So I wanted to just give a quick picture of what the sort of 3D data is available. So this is measurements of relative humidity from the ARES instrument on the Arcgis satellite. So a lot of the data is 3D, volumetric, and those are the types of data that work really well in these sort of immersive environments. So here we're looking at the ARES data on the northwest coast of Africa, at the like over Morocco and the Sahara Desert. So you can see the dust plumes coming from the desert. So some example XR software, one that I've worked on for a few years is called Sci Vr. So this is a fully immersive science data visualization application we built specifically for Earth scientists. So we want them to be able to explore the data sets within a fully virtual room scale environment. And this allows them to be able to use their natural depth perception. So seeing the data with stereo vision, being able to use their hands with controllers in these environments, and offering new tools such as a data slicer, being able to scale objects with your controls, and being able to query data values with a laser pointer. So we built this in Unity. For those folks unfamiliar with Unity, is a game engine or development environment usually built for developing video games, but you can also use it to build any type of software. And we built this originally for the Vive, which is a higher end virtual reality headset. So this was developed to help scientists better understand their data, to get quicker feedback on interacting with the data, and to hopefully improve their chances of making scientific discoveries. Important feature is to have collaboration. So being able to interact with multiple scientists within the same environment. Another feature that we found that was actually really useful in this case was being able to take advantage of the GPU to enable high performance real-time visualizations and on-the-fly computations. Do note this is not available with headsets that are standalone or not connected to a computer. So in the case of the Vive, it's connected directly to a high performance gaming PC. So we're able to leverage the hardware that comes with it. And in Sci VR, we're able to now interact. This goes for VR in general, but being able to interact with the data in ways that typical desktop cannot. So you're no longer confined to just your monitor, a keyboard, and a mouse, but you actually have this entire room with your hands and controllers to actually interact with the environment. And this was built for the Sea Level Change Portal and the Virtual Earth System Laboratory. They were the original sponsors of the Sci Vr project. This is a short video of how it looks like. This is from a perspective of, you kind of have to imagine a virtual person in there, but you can see the controllers moving around, slicing through an ocean model. So this is coming from the HiCom ocean model, showing a patch of, I think, somewhere in the Atlantic, but we're slicing through salinity, and you can quickly see, how far down the different measurements of salinity go within the ocean, and kind of uncovered what's beneath the surface, and not just at the top, really quickly. And skip to the next video. I think that's the same one. Here's another example. This is looking at data collected by Argo floats. So this is another global data set. We have basically a volume of the entire Earth, or rather its oceans. And normally, if you're looking at this data set with a 2D desktop, you're looking at the surface, but this lets you naturally just use your hands, flip to the side, and look at things from sort of an arbitrary profile and see what's beneath the ocean. So in this case, I was curious how far the El Nino anomaly extends beneath the surface. It's kind of hard to tell with this screen, but if I fast forward a little bit, we're kind of slicing, from the top of the ocean down to see how far this blob of ocean temperature anomaly goes down within the ocean. So this is another tool that lets you kind of squeeze the color palette to bring out the coloration more. So you can see it actually doesn't extend super far down, within the depths of the ocean, but it's curious to see something like that and being able to use tools like virtual reality. Lets you do these things really, really quick. I think I have one more video here. So this is just a few more examples. This is looking at a typhoon. This was captured, I think, by CubeSats, and we put this together on top of MODIS imagery that's coming from Gibbs, or the NASA Global Imagery Browse Services. So we're able to kind of add a 2D data set and then plop on a 3D volume on top, and be able to see data that way. I think there was one more data set at the end. So this is looking at a glacier in Alaska, the Columbia Glacier, and being able to extract data values from that data set. We also developed, in addition to VR, an augmented reality version of the software. So this is running on the HoloLens 2. The big complaint we got from scientists from using VR was motion sickness. A lot of folks aren't used to working with VR, but with AR, you're not completely immersed. You have an object in front of you, and you can also see your surroundings. So that helps alleviate motion sickness, and you don't have to constantly switch between a headset and desktop display. But the downside is we don't have as much computing power. So looking at this example, this is going to show the same data set. It takes a lot longer to load with the headset, so that's why I fast forwarded quite a bit here. So this is the same data set, but in the HoloLens 2. The quality is not as good, but you're able to see it in your physical environment and actually still use your hands to interact with the data set. So the big question here, does this really help Earth scientists? Well, we did find that it's been a great tool for science outreach and public engagement. We demoed this at several conferences, such as AGU, and it stirred up a lot of interest, got a lot of people really engaged with the data. A lot of the younger folks are really excited with the technologies. But does it really help you gain new scientific insights that you wouldn't otherwise if you're, just using your typical desktop? So we interviewed a few scientists. A some of their comments are included here. One is being able to draw quick insights just based on the sheer responsiveness of working with the data set. So you can see these 3D structures really quick, and you can take these iterative slices, and your brain just sort of patches everything together much faster. It's been really useful for collaborative discussion. So it's similar to having a lot of people, or a few people in the same room looking at the same thing and be able to point at a very specific feature and say like, hey, this is an unusual pattern, check this out. Which you can do over Zoom or some other platform with your cursor, but it's not quite exactly the same. And it's kind of hard to do that looking at three-dimensional data. This has been a struggle for scientists to use due to several reasons. In my opinion, the top issue is actually not so much the interface, but more how do I get my data into the game engine or into these virtual environments. So it's to kind of paraphrase a quote here, I want to quickly see this data that's available on the web, be able to bring it into the software without having to pre-process the data, configure a bunch of complex equipment. I just want my data set that I have here on my computer, plop it into the headset and see it, which is a lot harder than it seems. So a lot of the onboard compute power of the VR headsets are insufficient to just load, say, a 2 GB volumetric data file. You could do that if your if your headset's tethered to a computer and you have the GPU, but then you're dealing with the complex setup of having to hook up these devices into a gaming computer. And there's not a lot of services that can stream the data over the web. You're still often have to download a data set onto somewhere and then copy it into some other software. And neuroscience data isn't in formats like OBJ and FBX that are common with game engines where you can just drag and drop it and it'll show up in your software. They're in formats like NetCDF, HDF. I'm sure a lot of folks here at ESIP are familiar with those. And they're not easy things just to throw into any software and be able to visualize. The more general complaints like motion sickness, I think that'll go away with time, given improvements in headsets and computer technology. And there are more industry-wide challenges that I think are the industry will figure out eventually. So how can we sort of overcome the primary challenge? Well, I think we've done a pretty good job with developing tools and services for a 2D world. So one example, I'm a bit biased to this because I work with the NASA Global Imagery Browser Services and Worldview, is we developed these tools for EOSDIS, where you can just go up to a website and be able to see tons and tons of earth science imagery really, really quick. So I'm trying to, kind of think of an analog for that in the 3D world. And we also have things like cloud optimized geotiffs, another OGC compliant web services that can handle data streaming pretty well over the internet. Oh, and this is how Worldview looks like for folks who haven't seen it before. I encourage you all to take a look at it. But basically, you're able to load, in this case, sea surface temperature with some MODIS imagery, just by clicking and pointing to the layers that's available. So we developed a similar tool in augmented reality called Worldview Ar. This was sort of an experimental project, and we also try to gamify it, if you notice in the original menu. It's more of an outreach tool where, hey, we can do Worldview and AR. But the thing is, we're still working with 2D data. We're looking at imagery. We can take the imagery, if I fast forward a little bit, and use the texture and apply it onto a 3D sphere. And then you have a 3D globe of the world with imagery from Gibbs. Oops, did not mean to exit. So we went a little bit further and developed Unity examples with Gibbs imagery. So this is an open source repository that we have in GitHub that you can actually use open up the Unity project and add, it's showing demonstrations of how to access web map services or web map tile services and use it with Unity. However, like I was saying before, we're still only taking 2D data and just putting it into 3D environment, but it'd be really nice to have actual 3D data and be able to stream it into the metaverse. So there are standards that exist, including GLTF, 3D tiles, and I3S. And there are GIS software such as Arcgis Pro that can support 3D data and working with voxels. So there's a few examples here. The one on the bottom right is actually coming from ArcGIS Pro. And there are also software development kits that recently came out that lets developers work with, for example, ArcGIS maps in Unity or Unreal Engine, which is another popular gaming engine. And Cesium also has a developer environment for Unreal. At JPL, we developed, for the Mars missions, actually, Unity 3D tiles, which is a library that supports 3D tiles within Unity. So a lot of the current development that I've been involved recently is from the Gibbs perspective and other projects that I work on, is really focusing on building not so much the user interfaces and the interactive tools, but actually building the pipeline. So building, I call them 4D visualization services, because in most cases we're also dealing with time in addition to latitude, longitude, and height or depth. So we developed a few prototypes for Gibbs. We added support, experimental support for 3D tiles in Sci Vr so that we can actually stream the data into Sci Vr. But we've also had a lot of challenges working to support heterogeneous types of visualizations. So things such as terrains versus point clouds are very different, or working at varying scales. So we have data that's at a centimeter scale that's captured by an in situ instrument, or like the Mars rover, where we're looking at small rocks, versus orbital observations where the scale is at kilometer level or degrees of latitude. So those have been the challenges. I'm hoping to work through these with the community. And I think this is actually my last slide. So that is all that I had for my presentation. Thank you very much.
Thank you, Joe. That was an excellent talk. And one puzzle was solved. So what's missing from space station scene is live data that comes from like a Gibbs or NASA data centers. What they provided was a static scene, which was already captured. As Joe Roberts mentioned, those devices are very hardware limited. So you have to package all the data in as a single app, which is not that cool, in my opinion. In the future, like Joe's efforts, we may be able to really see what's going on in the almost real time through the space station. And next topic is about how to make VR easy through the ArcGIS. And next speaker is, Marcus Lupp from Swiss.
So I hope screen sharing works. Do you see my presentation? Yeah, okay. Yeah, welcome to my presentation about ArcGIS 360 VR. It's our new web app to make publishing from GIS to VR as easy as possible. My name is Marcus Lupp. I'm working at the Esri R&D Center in Zurich. And why would we want VR at all? VR is designed for 3D, so there is no 3D projection involved. And this means that you get a sense of scale of how big things actually are. And it also gives you a sense of immersiveness. So you can feel like you're actually there and see how big are those buildings actually. And this enables or enhances some GIS use cases. For example, you can explore sites all around the world while really feeling like you're there. You can evaluate project proposals, looking at some details. You can communicate new developments in your city to stakeholders. And one of my favorite use cases is to compare scenarios. For example, a city wants to redevelop some parts of the city. Now they can create VR scenarios and show them to people. And it's very easy to switch between those scenarios in our new tool. Now, it was already mentioned in the last talk, how to get GIS data into VR. That's really a challenge. What was mentioned before was mostly this route, where you have software that is installed in your machine. For example, Arcgis City Engine or game engines. And there you have to bake your data. It converts the Arcgis data to some game engine data. And this way you can get very high quality VR experiences, but it involves a lot of authoring of the scene, of optimizations, and multiple tools are involved. Now, what is new just with the latest release of Arcgis Online? We already have the web scene of a few years, but now what we also have is a completely web-based publishing path to Arcgis 360 VR. So Arcgis 360 VR already existed. We already had this with publishing from City Engine, but now you can do this completely in the web without having to install any additional software. How does this work? It's best if I show you, and to make it more exciting, I'm gonna try to do this live. I hope you can see my browser. Can you see my browser? I don't see the chat, so I just hope it's there. Yes, okay. So this is the 360 VR experience website, like it looked before already. And now we have this new button here, New 360 VR Experience. And if you click it, you get to the scene select screen. Here you can see all the scenes that are in your Arcgis Online account, or you can just go to all the public scenes. You can search for some scenes, for example, typhoons. And if you click on it, you get a preview of how it will look like in VR approximately. There are multiple layers in this scene. And you already see that it takes a bit to load. And you might ask yourself, why do we need this authoring and publishing process at all? Because it's already there. We could just show this in VR. It's just what was mentioned before, the performance. Even it looks quite fast, this whole loading time is still too slow for example, on the Quest. It's quite slow. So we need to pre-process this somehow to make it fast so you don't get nauseous in VR. And this is done if you click next. Let's just give this another name. And what it does now during this publishing process, it fetches all the data there is for this scene and compiles it into an efficient file that can be easily shown on a VR device. So specifically, we create 360 VR images. Of course, you have some limitations because of this. It only bakes the viewpoints or the scenarios that are actually there. So you can't move around freely. So that would be something for the future. The last part is actually uploading. So yeah, it's finished. So we successfully published the scene. What you can do now, you can open it in the viewer or view it in Arcgis Online. It downloads it, and now you see the scene is immediately loaded. There is no loading anymore, so it's very fast. Now, the important thing is, of course, we want to see this in VR. So what I'm going to try now is, I hope it doesn't crash now, to show it on my HP Reverb, which is connected to my desktop PC. Here we have this button, and if I click it, it should go into the VR mode, and I should be able to stream it here. Can you see the stream? I hope you do. Just look at the chat again. Yeah, okay, so it's there. And now with the controller, which is of course there and up now, I hope I'm able to bring up the menu. Bring up the menu and you see the same as we had before, but now in VR, it's different scenes. And it's perfectly smooth and there is no discernible loading time. But of course, this limitation, we only have the viewpoints that we have prepared. If I exit it again, it gets back to my web browser. Now you can also show this in different devices. For example, on your smartphone. First, you can also publish it directly from the scene viewer. That's just another way to select the scene. So you would skip those two select screens, click 360 VR experience here, which would get you to this point here. So that's just another way to start this whole publishing process. If you look at it on your phone, it looks like this. You have your video doesn't play. Maybe I'm just so streaming from the VR device works, but an Outlook video won't play. That's interesting. But essentially what I want to show is on your smartphone, it follows the movements of your phone, and then you can look at the scene, toggle scenarios, and it kind of looks like if you were looking through a window. And I think in the future, this would be a very interesting augmented reality experience. Now for the final one, the most interesting case in my point of view is on the Oculus Quest. The idea, it's very simple. You start your web browser on your Oculus Quest, select experience and click allow VR. That's one thing that you might miss. And then it immediately goes to VR. You don't need to install anything. And again, I'm gonna try to stream this live from my Quest. Let's see if this works. First, I have to start the stream on my device again. Of course, it stopped. Computer, next. It should cast it to my browser now. Do you see it? Yeah, I think you should be able to see this now. Okay. And if you want to show a VR scene now, what you're going to do is you go to your app library and open the browser. This is installed by default on the Oculus Quest. Open it. I have already opened the scene here. What you would need to do is just enter 360 VR, Arcgis.com, GS.com, and here you are. It's the same interface as you've seen before, and now we can select our experiences. We disabled the publishing button on the Quest because it would just be too slow. To show the experience I offered before, you can go to my experience, and the most recent one is going to show up here. That's the thing we published before. Now I open it and immediately we enter the VR mode without having to install anything. So this is still a web browser that's running here. I don't know why I have this weird blue area. Yeah. You can look around, change the viewpoints. And this looks actually really cool because it feels like the Earth is right in front of you. And it's very fast. There is no loading time when we run. It's the maximum frame rate of the Oculus Quest. And if I exit it again, it's completely seamless. You're back in your VR experiences browser, and you can open some other scene here. Let's just see what we have here. My favorites, maybe. The longest part is this downloading. We are relying on the browser cache. So if you have opened it before, the browser cache should serve it immediately, so there is no waiting time involved. But as soon as this initial loading is finished, where we fetch all those optimized views. There is no more loading involved, and it's gonna be hopefully a smooth experience. Yeah. In this scene, you have different zoning laws. You can visualize different zoning volumes. You can see them from different angles. And what we have in VR is those 3D cameras. They're actually georeferenced, and they show you where those viewpoints down there are. So they help you in navigating the scene. You can select different scenarios and visualize them. Okay, that was my live stream. Let's see if the video, my PowerPoint video plays. My next one. Apparently it's harder for PowerPoint to play videos than to stream VR. So what I've shown before was essentially, wow, everybody knows PowerPoint. I'm gonna open my Windows Explorer and start it from here. So you see the Oculus Quest works better than Microsoft PowerPoint. There should be my ASIP folder, and there should be some, maybe if I open it from a presentation directly. Wow, cannot play media. Now that is the first, I have to say. I mean, you've seen most of the cool stuff already. The last video I wanted to show you is some different use cases in VR. But because the streaming worked so well, you've seen most of it already, which the different scenarios. What I wanted to show you is some nice architecture visualization, where you see different kinds of, where you see a very high quality building that is planned, and the architect tries to present this to his client. One last try, maybe now the video starts. No, it doesn't. Okay. To sum it up, VR provides a great sense of scale. So this makes it great for scenario comparisons. For example, you've seen it in a zoning scene where you have the zoning volume and then different scenarios on how this might be developed in the future. With our new web app, it's very easy to publish those scenes. Just go to this website, and what we do is we publish web scenes to Arcgis 360 VR experiences. Those web scenes itself, you can author them also in the web using the S3 scene viewer. And then if you want to look at it, you can look at it in any web browser, on any VR device. You can look at it in your Quest, on your smartphone, on your desktop. Now, what was missing in those scenes is interactivity. So those were static viewpoints, and there wasn't any labeling and so on. So this is the big new feature we want to get ready for probably this October. We want to have pop-ups in there. So you can click on some objects, and then we query a feature service in the back, and you can see some information for those objects. For example, here, the wind speed of the hurricane. Yeah, thanks. That's my presentation. You're welcome to check it out on this website. I hope some Oculus Quests are live at your location, so you can try this out. Thanks.
Thank you, Marcus. Thank you so much. Yeah. Yeah, you are the first one who presented the Quest streaming service on EC. It was awesome. Yeah. Congratulations. And yeah, Marcus provided another missing puzzle from the space station mission, which is how to generate VR scene easily. And Arcgis can do so many things. And for example, I want to see my house from International Space Station, but didn't know how. But now I know, because Arcgis CI/CD engine, and with those web scenes, I can easily integrate that kind of thing in Metaverse application. So next speaker is Shayna, and she will talk about another missing components in the ISS mission app.
Hey, good afternoon, everybody. I'm Shayna Solis, formerly Skolnick, and I'm very sad to not be there with you in person. Unfortunately, I came down with COVID last week, so I'm kind of still recovering and couldn't be there with you in person. But with this great virtual technology, hopefully this will still be a compelling conversation and presentation. Let me get this started. So you've gotten a great introduction from some of the other speakers about sort of the state of the industry right now in terms of virtual, augmented, and mixed reality. And this is something that I've been working on actually since 2015. And Joe Roberts and I actually had a group in ESA for a while, VR AR for Science group. Kind of disbanded after a while, but maybe after seeing the results from today's session, it's something that we should resurrect and get started again. So I'm going to be talking a little bit about a specific use case. We've done a lot of different work at really exploring immersive technology, and I'm going to be talking about some of our more recent work focusing on disasters and some collaboration areas with NASA Applied Sciences. So like I mentioned, this is something that Navteca has been working on for quite a while. I'm the co-founder and CEO. And we started really exploring VR actually when the dev kits were still available before the commercial headsets were even out back in 2015. And got some really amazing early results, just being able to show people the actual size and shape of the continents. What does the ocean look like when you can see that the Pacific Ocean is all one thing and it's connected, and you don't just see it as somehow these two halves that are opposite. And from there, we had gotten some early funding from NASA, from the Earth Science Technology Office. And actually, I authored a study for NASA about these science applications. And we actually went through the Esri startup program. So we're very familiar with the Esri evolution of being able to support importing data and information into these type of platforms. And it's really cool actually to see, that was a great presentation to see, exactly where you guys are at with that. So one of the things that came out of that study that we did for NASA for Applied Sciences was a number of different use cases, and really asking the question, kind of what Joe has given us as the premise of today, what can you do differently in virtual and augmented reality that you can't do in traditional visualization? What does immersive technology give us that we couldn't do otherwise? And one of the use cases that emerged from that was really to look at disaster applications, because this is sometimes a disconnect between the data and information that is out there. We have so many different portals and repositories and visualization tools, but are they connected? Is it presented in a way where the people who are really sort of the boots on the ground, that last mile of information, is this in a format that is actually understandable, relevant, and actionable? So that was, the challenge that we've kind of taken on in the past couple of years. And the focus of our work is to really try to translate this information that's out there into a format using immersive technology that makes it available to people who are really needing it for decision making. So I'm going to take you through a little bit of that. And through this work, we've really started to see that this is the baby step, the little bits of development, getting towards a place where this type of game engine technology and then the output into virtual and augmented and mixed reality can actually increase resiliency. When we can help people visualize and plan and run out different scenarios and see the possible effects of things, then we can be really influencing having a positive outcome for the cities and towns and states and countries that are going to be dealing with ever worsening disasters, extreme weather, and of course being exacerbated by climate change. So to give you an example of that, we have a lot of different, work, so I won't take you too much through it, but just to give you an example, this is landslide data from NASA Goddard Space Flight Center. And when we bring it into the VR platform, you can see that we can bring in a lot of cinematography. So we can use lighting conditions, we can bring in wind, we can bring in realistic terrain, so that we now have the 3D geospatial terrain layered with the data, but then also these realistic textures, the actual building footprints, being able to see the agricultural holdings. This really brings this information to life for somebody like a city mayor or an urban planner or somebody who deals with public policy, who isn't necessarily accustomed to looking at scientific data or geospatial information. One of the things you've heard the other speakers talk about too is also the importance of being able to bring in real-time data or near real-time data. And that is something that NAFTECA has been successful at. It's been a huge goal of ours to really make this a technology that could be incorporated into a decision-making workflow. And to do that, you really need to be able to bring in new information without having to go back and code something or have any kind of developer involved. So one of the first steps in this process, sort of starting in 2019, was to use APIs and really try to access information via outside repositories. So one example of that was connecting the NASA Disaster Applications public-facing portal, which uses ArcGIS Online as its backend, and connecting that to the VR platform and connecting that to Unity Game Engine. And actually in 2019 at the Esri user conference, it was just mere days after the Ridgecrest earthquake hit in California. And as soon as the information for the radar of surface land displacement was available in the NASA portal, simultaneously, we were actually able to demo it at the user conference in real time in VR. So very cool achievement to be able to do that. So in that vein, I wanted to share with you an example of, how can we connect a data product that is out there with the game platform. And again, this is, all achieved through API development. This is an example of a NASA data product. It's called the Global Landslide Nowcast. And it is updated every 3 hours, looking at lots of different parameters to give up-to-date information about landslide risk. There's lots of different precipitation data, soil moisture and such that goes into it. And this example is from a project that we did in Guatemala City, looking at different types of risk for the region. They also have heightened seismic risk. And so of course, being able to then have information about landslide potential, whether it's caused by extreme rainfall or by seismic activity, would be very useful for people who are involved in emergency management and preparedness in the region. This is a snapshot in this video that I'm showing to you. If we were to look at it now in VR, we'd have the real-time information coming directly from the portal from that Global Landslide Nowcast data product. Because really at the end of the day, what we're trying to do is link that information, to the people who are on the ground, who are engaging in preparedness exercises, who are trying to make their communities more safe and more resilient by giving them the information that's already out there. And then of course, for the organizations themselves, whether it's NASA, NOAA, USGS, international groups, they also have a mission, which is to make their data more open and accessible. And we think that platforms like this, like gaming engines, like immersive visualization, really contribute to those goals of making the information more available, more accessible, and more understandable. Here's another example. This is a different type of information. This is looking at flooding. This is from a NOAA data product. And It's called the slosh model. So it's looking at potential for sea level rise. You may recognize Lower Manhattan. And in this example, what we wanted to do was show how we could translate information that is normally discussed numerically, whether, storm surge, sea level rise, these numbers get thrown around, whether it's, 20-foot storm surge or 2 meters of sea level rise. Well, what does that mean? Unless you can actually see it in a place and actually see specific buildings and specific roads, specific infrastructure, then it's somewhat meaningless, because we really need that 3D terrain and we really need that context. So this experiment was translating the output of the slosh model, just using NOAA's web-based tool, and turning that into a realistic water texture using the Unity game engine. And then you can see here in the video that the user with the VR controllers is able to adjust the water height, toggle the information on and off. So when we're seeing the orange and blue, we're actually seeing the coloration from the scientific model, or just turn it into, again, that realistic water texture. So if you're showing it to somebody who doesn't necessarily have the science background and just wants to be able to see what it would look like to have these streets flooded, then they can look at it that way as well. In a fully functional tool, you would be able to bring in lots of different data layers and toggle them on and off, change the lighting conditions, day, night, seasons, et cetera. And those are all things that we're working on. So going back to that Guatemala City project, wanted to talk a little bit more about that, because I think it's really been an amazing pilot, kind of showing where we can go with this. They had a multi-hazard risk analysis done. And again, they have seismic risk, both from earthquake and volcanoes. They have flooding risk. They're susceptible to tropical storms and cyclones. So of course, that then brings landslides. And so they had a whole array of things that they wanted to look at. But the report was very dense. Lots of critical information, but not necessarily easy to understand it or understand how it would be applied. Also, lots of maps. And so this is an example of some of the things that were in the report. And, you can see, again, this would be challenging for a city planner or engineer to put into action. This is a map showing all of the earthquakes and important seismic activity over the last 1,500 years in Guatemala, and, being able to see where the fault lines are and such. So we really took this on as a challenge to translate this information into the game engine platform to help people in the region to understand the critical nature of this report and potentially be able to use it for some better decision making. So I want to give you an example of what that looks like in the game engine. So we created this, using obviously the 3D terrain. The yellow are the fault lines, correctly located. They were very interested in understanding the potential impacts to the international airport and also to the central city corridor, which is, of course, the hub of economic activity, social activity, healthcare for the region. The 3D buildings that you're seeing, this was an interesting asset that the city had. They had 3D models that were being used for property taxation. They weren't using them for emergency management. So that's an example of how you can bring in lots of disparate information. It's not necessarily just the scientific data, but also looking at what other assets can be brought to the project. You can see like the football stadium, local landmarks. So this is a way to give people that situational awareness that they may be missing by just looking at a traditional map or a traditional visualization. When we were showing this to city officials, there were so many times where they just said, oh, aha, I get it now. Now I see this. Now I, understand where we should be focusing our efforts for coming up with better evacuation plans. Or now I see that our refuge areas that we've set up, actually aren't in good places, or we can really see heightened landslide risk because of understanding the terrain and the amount of buildings that are, precariously placed on these cliffs, being able to see the volcanoes and overlaying air quality information and sort of seeing the susceptibility for the region. has been, really eye-opening, I think, for everyone who was involved in this project. And then, of course, being able to look at it in different formats. So all of this was done during the pandemic. We weren't able to go and put headsets on people's heads. So what we did is we actually created these type of videos as 360 movies and sent them out to people's mobile devices. So they were still able to have a sense of immersion, a sense of interactivity, even without the headset. And that's definitely been a focus for us, throughout the pandemic, is taking advantage of the underlying game engine technology and not being limited to what you can do in a headset. It's great if you have one and you can look at it that way, but it's not necessary to still derive benefits. So that Guatemala City project ended up being, really exciting, and they were able to use our information as part of an earthquake simulation drill, sort of like what California does with the great shakeouts. And this took place in February, and you can see NAVTECA's visualization here in the Emergency Operations Center. They brought together, this was an international effort, 7 different countries, including the United Nations, and to be able to use our visualizations to help create that situational awareness, really setting the stage for the simulation drill, was really, really exciting, to see how this could be used in a real world application. So just to kind of wrap up with where we're at currently, we've really started focusing on a different type of disaster and looking at wildfires. Again, we've really seen that there's a gap in the data and information that's out there and how it's being used by the more boots on the ground type of organizations. And through the new NASA wildfire program, we're starting to create these collaborations. So this is just a little sneak peek, a taste of what we're working on. Again, using all of the cinematography, amazing, lighting that we can get, and bringing that to bear by combining it with actual data, real information, real terrain, so that we are creating an incredibly realistic model of what someone might encounter in an actual wildfire. So the smoke plume and height, this is all point cloud data, but represented visually in a way that people can relate to it. That's the next one. So again, these are very new. We're working on being able to generate trees according to the landscape, and so making sure that those are correct for the region. You can see here, we are experimenting with understanding how wildfires spread and being able to show hotspots and embers as they pop up. Again, with the wildfire, it's important to be able to get the lighting conditions right. A lot of times smoke will obliterate any natural light. So, we've heard from the firefighting community that this is really great to be able to see it this way, because it's more realistic, to be able to see data represented in a way that somebody who's had that experience on the ground can really relate to it. So we think that, again, these are baby steps towards creating a real tool and a visual framework and platform to be able to bring this type of data and information into a setting that people can use it, so that they can incorporate it into decisions, so that they can be better prepared and really create that resiliency, be able to use the information that's out there, and be able to connect the dots between lots of different types of information, data repositories, geospatial, and really bring that into a format that is collaborative. So no matter what your background is, whether it's a science and research background, or more of that emergency operations, or even a politician, somebody who's responsible for decision-making, really giving people that common visual framework to be able to look at information, understand it, and make decisions. So with that, I'll wrap up my portion, and thank you so much. This is my contact information, and I'll be open and love to continue this conversation. Thank you.
Thank you, Shayna. That was a great talk. And from Shayna's presentation, we learned that one of the missing pieces was about human and action and society. So yeah, Metaverse can unify almost anything you can imagine. The final presentation is by David, and we'll find out another missing piece from the mission International Space Station through his talk.
Hey everyone, give me 1 second, I'll share my screen. Can everyone see my screen? Take that as a yes. Okay, great. So let me just check the chat. Wonderful. So my name's David. I'm the CTO at dClimate. Thank you to all the speakers. Unfortunately, my presentation won't be as visually impressive, so I'll ask you to lean a little bit more on your imagination, since this is more on the data side of things, on the data infrastructure. But the theme of this is making the metaverse fungible. And the title of this talk is Building the Infrastructure for Regenerative Finance. I know it's a lot to unpack, so given that this topic covers many layers of abstractions, which some of us sometimes forget when talking about it, I'll first introduce you to some concepts which some of you might be familiar with, some not. But my hope is to give you all a strong foundational understanding in order to provide the tools you need to not only begin to understand how this ecosystem is evolving, but ultimately also how to begin contributing. So with that, we can begin. So what is blockchain? I'm going to gloss over some things here to keep it brief and probably miss some nuance, so bear with me. For some, it needs no introduction, but ultimately, a blockchain's most simple form is just a continuously growing list of records. Within this list of records, there are batches of transactions known as blocks, and these transactions within the blocks can, for example, track the state of a balance between users. I'm sure you guys have heard of Bitcoin before. Each block refers to each previous block via hashes, aka using math, to ensure message integrity. In other words, if a malicious actor tried to change the state of one transaction, all the subsequent transaction states, in other words, the hashes, are invalid. For those of you familiar with data structures, you'll recognize the blockchain as an append-only linked list. This data structure or blockchain is then duplicated and distributed across an entire network of other computers. In other words, it becomes a distributed ledger. The state of this ledger cannot have its history changed. Caveats there, of course, but it's mostly therefore immutable, and any addition to the state need to adhere to a set of rules known as a consensus algorithm. So some of you might be familiar with proof of work, proof of stake, and other consensus algorithms that exist. The reason this is so important is because it allows individuals who do not know or trust each other to exchange value with one another. To paraphrase Andreas Antonopoulos, blockchains enable the internet of money, and by extension, the internet of value, both tangible and intangible. A little bit of foreboding there. So what is Web3? Web3 is often used as a catch-all term, but ends up being very nebulous to those not online 24/7 like myself. I found this tweet which kind of sums it up quite well. For those of you old like me, you'll remember Web 1, which only allowed you to read content. Web 2 allowed us to begin posting content on sites such as on MySpace and Facebook. And Web 3 allows us to be owners of the content we publish, including data, right? So I'm often asked, what role does Web3 play when it comes to solving real world problems? Shana definitely brought that up, right? Making this data actionable. In other words, data that creates a material impact on the physical world outside the insular and niche speculative economies some of you may hear about in the news or in certain tabloids about Web3. Web3 at its core provides a way to trustlessly coordinate and incentivize particular behaviors while also giving those who participate a share in the economic upside of the results of such coordination. So you'll hear terms thrown around such as DAOs, tokens, game theory, composability, credible neutrality, decentralized consensus, censorship resistance, and many, many more, including Metaverse, right? All of which describe or encapsulate some characteristic of Web3, but ultimately Web3 is just a suite of technologies that enable a distributed group of agents, people or machines, to agree and act on shared truths, which ultimately is just state, right? So just to get some minor things out of the way, some of these technologies are more centralized, which means or can be defined as the ability of a party to unilaterally decide an outcome than others, but they all play a role in enabling some level of communication. So there are various trade-offs that come with different levels of centralization, such as speed or throughput in exchange for security, which must be kept in mind when designing systems that have a real world impact. And I promise we'll get to that soon. In some cases, the trade-offs are worthwhile, but in other cases, they must be scrutinized for safety, as the open source systems are not totally trustless, but rather trust deferred. You defer your trust to the integrity of the system. In other words, that there's no bugs, right? To the rules that govern the code that you use, or the custodians that manage how that code is executed. So a key term in the Web3 space, in particular this place known as DeFi or decentralized finance, is the word known as composability. Due to the open source nature of Web3, in other words, all the code is open source, all the code can be read by anyone, all the code can be executed by anybody, including code that somebody else has deployed, of course, depending on permissions that have been created. But this means that anybody can also call value, or in other words, build on the shoulders of others. So interoperability and composability are at the core of what's being built in Web3. In this image, you can see various layers of applications being built on one another, known in the common language of DeFi, known as money Legos, because things build on top of one another, and they are known as primitives that can stack within one another. So you have your base layers, then you have your financial plumbing or tooling, you have the things that allow you to then take loans against that money, and so on and so forth. Ultimately, the goal is we'll hopefully see this in the world of regenerative finance, remote sensing, and so on and so forth, but I'll leave that for later. This is the Web3 stack. Now, I talked about blockchains before in the context of Bitcoin, where a balance state is updated. What if I told you can update states other than a balance, such as the temperature in Los Angeles? The smart contract-enabled distributed ledgers, some of us may know, such as Ethereum, provide a base layer for communicating agreement on some state, while also executing logic on that state. And that point is critical, right? You have state, and then you can now do some logic on that state, which is distributed and immutable. So the state may represent something with economic value, an intrinsic value, such as a token backed by a dollar, right? Just dollars in a bank somewhere, and you could tokenize that and represent that as state on the network, which represents that dollar. Or an NFT, a non-fungible token, which can represent some asset in the real world. Or it could be something totally intangible, such as the results of the game. But what's critical to understand is that this shared truth is bound by a set of rules that are completely transparent and can be verified by anyone. These rules include math and cryptography beyond the scope of this talk, but they oftentimes can also determine how centralized something is. The combination of these rules and the consequent shared truths have allowed us to create the financial plumbing and tools / instruments to exchange value. The representation of this real world value on chain can, in many instances, be known as tokenization, which many of you may have heard of. Similarly, the combination of these rules and shared truths via distributed ledgers have enabled the creation of base layer tooling or primitives to store, execute, or share types of state, which were prerequisites to solve the actual real world problems that we care about. Some of these include Chainlink, an Oracle network right here, that provides a trustless bridge for bridging real world data on chain, which dClimate uses extensively, and I'll talk about what dClimate is in just a little bit, along with storage protocols such as IPFS, which you can see right here, that allows dClimate to store 40 terabytes of climate data. Again, all of this is decentralized technology, so there isn't one single point of failure. The data is distributed and it's immutable, so it cannot be changed by anyone. And because of its distributed nature, it also costs far less to provide this data to users who want to use it. So kind of gave you guys the background of what blockchain is, a speed run through that, through what is Web3. Now this brings us to regenerative finance, refi. Everyone has their own definition of what refi is. The term itself has existed prior to its popularity and usage within the broader Web3 ecosystem, but here are some quotes that resonate here with me. So regenerating means restoring, renewing, and replenishing in addition to conserving. This is from Walmart's website, a very great article talking about regenerative approaches that go just beyond sustainability, but building back what has been lost. Also, another one here that I really liked was regenerative finance uses money as a tool to solve systemic problems and regenerate communities and natural environments. Its goal is to heal and create shared value. Profits are not the end, but rather a means of further progress. And the reason why this is very important is because blockchains, as I mentioned before, allow users to share state with one another in a trustless manner, right? You don't need to trust that somebody else is doing something appropriate on the network, because the math enforces that, right? So you know the value that's already there, which means that with blockchains, you bake in value exchange already into the blockchain itself. In other words, you have payment rails that live alongside data. prior to that, you need to plug in, let's say, a Stripe or something else here. You can now create value for the data that you already have there. So in the context of Web3, refi lives at the intersection of climate and crypto. It means leveraging the open source nature, composability, permissionlessness of Web3 technologies to direct capital affecting real world positive climate impact. So here's an image created by Gitcoin, and it's a map to illustrate the areas and projects being worked on in general areas of refi. It doesn't have all of them. Every day there are new projects that are working to better the world in some way, shape, or form, especially in the areas of climate and climate data infrastructure. So as a total aside, Gitcoin provides millions of dollars of funding for public goods, of which regenerative finance is a critical part of. Through novel methods of funding enabled via blockchain, such as quadratic funding, to get a more fair distribution of funding to projects, whether it's planting trees or creating new GIS remote sensing software. I'm sure after the talks that I've just seen, there will be many grant proposals that will be made to hopefully develop on all the amazing things that you guys have been building. So the problem, which is somewhat meta, is you can't solve a problem you can't measure or understand. And that's something that was brought up as well by previous speakers, right? Because in order to make data actionable, you need to kind of understand what that data is, and even what is, like, where is that data coming from, and all the information that goes along with it, right? So blockchains are good at valuing public goods. They provide transparency and immutability guarantees while remaining trustless. As a result, they also provide a way to value tangible, intangible things amongst individuals. Combine the ability to create traceable and verifiable data while making it accessible, you now have the ingredients for meaningful climate action. I will get to that in just a moment, Sheena. I'll leave the questions towards the end, but it's a great question. So what is the MRV? Some of you might be familiar with the MRV abbreviation, which is measurement, reporting, and verification. And I'll leave the wall of text that you guys can read later, but essentially it entails collecting and recording information for generative actions, right? This means sensors in the field, ground truth data using maybe IoT sensors, or remote sensing, satellite imagery, LiDAR, so on and so forth. The reporting aspect is collecting that data, compiling it, collating it, and then standardizing it according to methodologies that other people can then use, right? And lastly, and one of the most important parts of this is verification, the ability to have this data available for third-party analysis and verification, right? You want an independent assessment to be able to be run on this particular data to know whether it's been manipulated, whether it has some statistical anomalies, maybe the sensors were off, needed calibration. But ultimately, the goal here is you can do this in a decentralized way. So instead of having centralized parties, centralized failure points to do this, the entire collective community can work together towards MRV solutions. So why is the MRV important? I kind of spoke to it a little bit already, but one of the biggest reasons, or one of the most important reasons why, is that it's one of the biggest bottlenecks to scaling climate action. If we have the ability to do things on chain and we're able to, exercise some sort of contracts based on this data, or let's say measurement of carbon or forestry growth, ultimately this boils down to being able to measure this data. And so if we don't have this data at scale, then we can't solve these problems at scale. So having the ability to do all this MRV, especially in a decentralized way where there are centralized parties who can be failure points, then we can all grow together and work much faster to solving the problem, which is hitting us. So this kind of brings us a little bit into DClimate. And what is DClimate, which is the company that I'm the CTO at? It is a decentralized climate data ecosystem that currently includes a climate data marketplace, carbon offset portal, and a nascent incentivized IoT sensor network to map ground truth while laying the foundation for a do-it-yourself climate community. I'll speak on that in a few slides. So I know this was already talked by a few of the speakers, but some of the problems that exist and some of the problems that we solve is that there are large gaps in climate data. Some areas lack high resolution coverage for weather, pollution, so on and so forth, hampering economic development. Technical standards are in some cases haphazard, or there are bespoke standards that are used by different data providers. And it's very hard to collate this into one place, particularly because there's no real marketplace. You have to go to different FTP buckets, different universities to kind of put this data in one place. So it's very hard to find the things that you're looking for, especially in the formats that you need. It was also brought up, I believe, by Joe, the ability to stream data and cloud optimize approaches towards this. And this is something that DClimate has been working on, the ability to provide very large data sets, but then only the sections that you care about of these n-dimensional arrays. And we hope that most of this will end up being used in visualization tools and things like the Quest, where you can now stream this data straight from decentralized technology such as IPFS, decentralized storage, which again, there's no central failure point. And because it's not on an S3 bucket in, let's say, US East, and you're located, say, in South Africa, if your neighbor has an IPFS node, then now you'll get that data right from them. You don't have to travel halfway across the world in terms of data. So there's faster response times and less latency. Lastly, there's a lack of incentive for innovation in traditional space, right? It's very hard to compensate users in different countries who maybe don't have bank accounts. It's also hard for people to coordinate these things because the payment rails or the value exchange doesn't necessarily exist. There's no real way for people to monetize this data. Let's say they create or they collect a new data set. It's hard for them to be able to put that in a place which allows them to, either connect that with other data sets or be able to monetize what they already have. And that means not only monetizing it, let's say, in an NFT or a non-fungible token, but then being able to collateralize against the future cash flows of that, right? And then being able to implement this into new financial plumbing that is currently being built within the Web3 space. So I'm not going to go too deep into these, but the climate ecosystem are some of the apps that we have here. Stormbroker, it's not as serious as the rest of them, but it is a game which uses historical hurricane data in order to test your mettle to see how good you'd be a real estate investor in these particular areas, especially with respect to insurance. So this is a cool use case of the data that can get people sort of to know how useful this data can be outside of just the traditional ways in terms of insurance or things like that. Worksite is another interesting app, which is very useful, especially in the construction sector, for people to be able to predict how weather can impact the days that they can do work. Let's see, we can move on to the next slide. So yeah, I talked a little bit about the marketplace. This gives you all a little bit of a preview as to what we're building here. And again, it will make a central, decentralized, indexable area where you can find the data that you care about, and then also hopefully visualize it, right? You can see a little sneak peek here about the map, but our goal is to implement a lot what everybody has been working on here, where you can ultimately investigate, discover, and pretty much walk through the data in a 3D way in the not too distant future. But first, of course, we're starting with the base layer, which is the marketplace itself, to be able to find the data that you care about, especially in the formats that you need. So declimate data infrastructure, this goes a little bit more into the nitty gritty. So I won't dive too deep in here, but essentially what people should know is that there, again, is no centralized failure point. We're using this infrastructure technology called Chainlink, which again bridges real world data / IPFS here, which is where we're storing the data, and Filecoin, which gives you file permanence. So let's say you didn't pay your S3 bill, it's okay if you've been using something like Filecoin where you pay ahead of time for many years of file storage, that data will always be available. So even if a company shuts down or closes, that data remains. And not only does that data remain, it uses this thing called content addressable hashing, which means that the binary data itself is hashed, and that is how you find the data. You find it via its hash, not via location, via an IP address, but actually via the hash itself on the network. And so that means that if the data changes, so does what you look for when you go to find it. In other words, when you have that hash, you're getting that data back, which means that you get immutability out of the box. You know, the data cannot be tampered with, it cannot be changed. And so this is something that is of extreme importance, especially when you have mission critical applications that rely on this data. So we talked a little about the DMRV aspects of blockchain, and I want to highlight a little bit about how this can help when it comes to carbon sequestration and carbon monitoring. So when it comes to onboarding carbon offsets, it's a very lengthy process to gather the ground truth and certify projects. With DMRV, you're able to speed up this process and improve it tenfold, because you're able to use satellite imagery in order to be able to verify, let's say, some of the biomass or above ground biomass in general, which can help to better understand what the carbon sequestration potential is within a particular area. So this pretty much allows you to go to advanced satellite imagery, machine learning algorithms, in the on-chain carbon verification, which occurs in a decentralized way. In other words, the models are open, the data is totally viewable by anybody, and the way that it's executed is also can be executed by anyone, versus In more traditional methods, these things are more closed source. They're not accessible to the public. Not everyone can be a validator, let's say, for this data. So this is where we hope some of these things can definitely shine. Another app that we've built is Espresso. Again, this relies all on our distributed data on IPFS. There's no one centralized party. If you're running an IPFS node, you will also be able to start mirroring this data. And this Espresso app it pulls standardized data sets across many different countries for the potential of coffee production in various different areas amongst many different attributes, so that users can better understand and manage weather impacts in their day-to-day operations. I have a little window here where you can select the tree type, the country, the region, and you can see some of the graphs here that can provide some of the information, especially for those who are coffee producers. So let me skip to the next slide. This is where things get really interesting to me, but I wanted to provide you all with the background information to understand what can be done. So that was just a brief taste of what we're working on, but the opportunities in refi are endless. I'm listed here are some areas being worked on with some ideas you can build on with or develop further. So there's parametric insurance, right? That's how we were incubated. That's how we were started. You have the ability to hedge risk, especially for individual farmers when it comes to flooding, via parametric insurance. In other words, you don't have an insurance adjuster come in to check to see whether or not the damage is what it is. You can do so via satellite imagery, right? You can have certain parameters that can execute on its own in a decentralized way, autonomously. And so this reduces the overhead that insurance companies have, while then meaning that they can increase the payouts to individuals, and they can also scale their operations. DMRV, of course, is what I talked about before, but there are many other projects in the space. One in particular, which I like, is Open Forest Protocol, which we're validators for, that measure forestry coverage across the world. And it's a network of validators that all run their own different methodologies. And the idea is that in a decentralized way, you can all come to an agreement as to what the forest cover is in the area. You have things such as carbon offsets, such as Toucan, which bridge off-chain offsets on-chain and then fractionalize these so that you can now create a liquid market. So you have an actual price to carbon. Not only that, now that you have a tokenized version of carbon, you can then start doing things such as carbon-backed stablecoins, which is what Kumo is doing. There are natural capital assets in which you now have the ability to tokenize biodiversity from the real world on-chain. And so this means, again, you can issue stablecoins against money that is solely backed by the things that we know have a true impact on our planet. One of the other interesting areas that I'm super excited about is sustainability-linked bonds, where you can, and this has been pioneered and written about by Astral. I suggest you guys all visit their website. They have a really great pilot on the work they were doing there. But essentially, you can imagine a local municipality that wants to reduce, let's say, particulate matter or pollution within an area, right? What they can do then is that they can create this bond on-chain that uses on-chain data to be able, I'm so sorry, there's a little bit of background noise here. And what you can do is you can issue these bonds, and then based on the climate data parameters that you have, let's say pollution, particulate matter, you can increase or decrease the interest rate in which that local municipality has to pay it back. So you now created an incentivization structure that is based on real world data that also has a real world financial impact. And so these are the things that I'm very excited about. There's financing as well, the ability to offer loans to coffee producers that, again, use on-chain data that comes from the off-chain world. And so once you have this bridge, you're able to pretty much grease the payment rails, so to speak. Beyond that, I hope that many of the projects that we just saw would plug into a lot of decentralized technologies such as IPFS, again, where you don't have one centralized area for data storage, but rather a distributed network of nodes that can all provide this data, which can help speed things up and provide, let's say, cloud optimized files that will improve the streaming, the bandwidth needs of the different applications that are being built. So that's pretty much it. I hope you guys can start building on DClimate. We have an API with a ton of data that you can use to get started that I would love to maybe even see visualized. And that will be the next steps that we'll be working on as well on our end. First, we'll start with 2D, of course, but then 3D is what we have in mind. So that's pretty much it. If you have any questions, I'm more than open to answering them. I will first start, though, with Shayna's question, which is, I'll read for anyone who cannot see it. Blockchain is quite energy intensive. How do we square that with climate change and earth science? It's a really great question. So ultimately, the energy demands of the networks depend on the implementation of the network. So when I talked about the consensus algorithms before, there are some which are proof of work, right? Which is Bitcoin. Some of proof of stake, which don't rely on computational cycles being run in order to provide that hashing security, right? So this means that there's an energy reduction. In the case of Ethereum, there's this thing called the merge that will be occurring later this year that will be migrating Ethereum from proof of work to proof of stake. And so this will heavily reduce the energy demands to essentially just the computers that are processing transactions without any wasted work. To give an idea in terms of the comparisons of the energy that's being used in ecosystems, I believe something like the streaming of YouTube and gaming is something like 4 times or 3 to 4 times the amount of the Bitcoin network. And Bitcoin network is very energy intensive. But of course, with the move to proof of stake and other consensus algorithms, you will definitely get a heavy reduction in energy usage, while at the same time getting all the guarantees that come from using this technology. Not to speak of the energy usages of banking and all the other industries, which are very difficult to even ascertain with the current technologies due to the opaqueness that exists. Thank you, Shane. Guess I'll stop sharing there.
Joe, you're on mute for those of us who are online.
Yeah, so that whether that image really came from NASA or not, but there's no way to verify, right? But the climate platform like blockchain technology can help. So that was the last missing puzzle. And it's now 3:27. We have about 3 minutes to go. Oh no, we end with some slides.
The end of my question. There is some questions or?
Oh, is there a question?
I just said at the end of my talk, my Zoom crashed and I didn't hear anything. Were there some questions to my talk or?
So any questions from audience or no? Okay. So yeah, thank you for attending the first Metaverse session at EC, and hope you enjoy these talks, and we can talk about more in the future. Thank you. Thanks, guys.